Okay, let's get started. Hello, everyone. My name is Dr. Nagman Khan. I'm delighted to welcome you to this EDSL webinar on upcoming features for daylighting and climate-based daylight analysis using TAS. It's something you would have noticed from the series of recent webinars. There's a big emphasis on new features, new and exciting developments that you'll be hearing more of directly from EDSL. Let's take a quick look at the agenda today, and then I will hand over to the speakers to introduce themselves. So we're going to start with daylighting in TAS, the existing features you may or may not be aware of. I myself have only seen some of the very cool reporting features just recently, actually. And then Andrew will talk us through some analysis capabilities and workflow, especially looking at geometry for large and complex models. Then let's get on to the climate-based daylight modeling and results viewer. And then we'll take a look at a larger case study with some automation and optimization. You might remember we did a webinar on the GenOp tool a few months ago. So we'll be showing that and how that pertains to daylighting and shading today. And then exciting is the upcoming features that will be launching soon, and we'll give you an overview of that, and we can take some Q&A. You can post your Q&A in the chat or the Q&A panel here on Teams, and we'll be sending a recording of this webinar to everyone who registered in a couple of days. Let me hand over to our speakers today, and we'll kick off with Ian and Andrew.
I'll go first. Technical Director, EDSL. I'm down as a presenter today, but Andrew's going to be doing the vast bulk of the presenting. We'll probably just chip in the odd comment from here or there. So yeah, Andrew.
Yeah, and I'm Andrew. I've been with EDSL for almost 12 years, and I've got background in physics, and now I'm a software developer and director. So let's start with just a brief history of daylighting in building simulation. And Ian will know this probably better than me, but I did some research, and I
wasn't born in 1895.
not in 1895, but yeah, I found that's when the idea of the daylight factor was first introduced, and it's quite a good metric because it's quite a simple metric. It uses an overcast sky, and it's independent of the orientation and weather and time of day, so it's quite good for comparing designs. And it's just a simple ratio of how much daylight there is inside the space compared to outside. And then later on in the 1960s to 80s, we had some methods developed to actually calculate the daylight factor, numerically. So we had the split flux method, which is quite a simplified method. It basically accounts for the average reflectances of surfaces and roughly how much radiation goes from one surface to another surface, and so forth. And then we have a more complicated version of that, radiosity, which is an analytical solution which accounts for the flux transfer between all the different surfaces in a space. And then you've also got ray tracing, which is kind of a brute force method that literally casts rays around the space and follows them around to estimate the amount of illuminance. And then in the 1990s to 2000s, these methods started to get integrated into specialist tools and into building simulation tools. And one of the main reasons these calculations became of interest were because of the impact of lighting on a space inside the buildings. So before LEDs, the lighting gains were actually quite significant within the space. And they could reduce your heating demand or cause your space to overheat. So it was quite important that they were modeled properly in conjunction with daylight control. That was partially what drove that. And then later on in the 2000s, we had Ward and Reinhardt. They pioneered climate-based daylight modeling, the idea of sampling the space throughout the year, taking into consideration weather. And then Mardeljevic, so Reinhardt produced DaySim, which is the first tool that could actually calculate the CDM metrics. And then Mardeljevic, he pioneered the use of the UDI metrics, which really helped with the adoption, and did that work using DaySim. And in parallel at the same time, the glare metrics, they kind of followed a similar sort of development timeline. So people started to become interested in glare metrics, not just point-in-time glare metrics with a fixed view, but sort of annual glare metrics, which were quite useful for quantifying the risk of glare throughout the year. And yeah, you can see an image here of how here on the left you've got a simple daylight factor, and on the right you've got an image of one of the UDIA metrics from CBDM, which says how comfortable the space is throughout the year, taking into consideration that weather.
Sorry, just to butt in, Andrew, it's quite an interesting parallel there, because if you think about thermal modelling in buildings, that sort of went from steady state and sort of almost hand-based calculations, and now we're sort of looking at a much more dynamic approach where you're looking at every hour through the year, and it's almost like the daylight calculations have done a similar thing, initially hand-based calculations, which you then got better, and obviously then take the whole year into account.
Yeah, and even though we've moved away from these really warm, inefficient lights, we now have very efficient LEDs. We've also discovered that the amount of natural daylight a space gets is very important to a person's perception of the space, their productivity and their well-being. And so it's still of great importance trying to maximize the amount of natural light without making the space too bright and uncomfortable. So I'll start by going through what we have in TAS at the moment and what you can do in TAS with the current daylight implementation. There's actually quite a lot to it, and there's quite a lot to cover. So I'll try not to go too quickly. But I'll start by describing the methodology that we have. So for our daylighting in TAS, we use a package called Lightworks, which we've integrated into TAS. And it is a radiosity and ray tracing based solution. So it's not one or the other, it uses elements of both. So the main advantage to radiosity is that it's really, really good for accounting for diffuse shading. And it does that really, really well. So on the left here, you can see an image which is on the Wikipedia page for radiosity, and it just shows a simple direct illumination of the scene. And then on the right here, you've got the same scene rendered with a radiosity solution, and you can start to see like shadows behind the pillar, and you can see nice soft edges to these sun patches from the windows, and you can see reflections around the space, and that's the diffuse shading there. And then I produced a similar sort of image in TAS using a similar sort of model. It's not exactly the same, the view's not exactly the same, but you can see that when we do our full solution here using radiosity, we get those similar sorts of effects, but we also get these really nice sharp sun patches on the ground there, and that comes from the ray tracing contribution from the Lightworks engine as well. So we kind of have a benefit of both, which is why we chose Lightworks over simple ray tracing, which was not very good at accounting for the diffuse shading, and it's also very, 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 very slow.
Yeah, because ray tracing, you're effectively taking a sort of like a single photon, if you like, or a sort of modelled photon, and then projecting it into the space and then watching where it bounces. And I think if it's a specular surface like most are, so if it's not ultra shiny, every time one of those photons hits that specular surface, it has to turn into multiple rays bouncing off, because obviously you have to take into account the roughness and all that kind of stuff. And then each one of those, when they hit another surface, you get another multitude of rays. So it's a hugely non-linear and sort of massively expanding way of doing it via ray tracing. Sorry to butt in, Andrew.
No, it's useful. So I'll show you the first sort of, I mean, it's not kind of daylighting. Shadow analysis is the first thing that you might want to look at with TAS. So this is our training course model here, and it's quite a nice simple model, and it's got an external shade here. And if you want to look at shadows in TAS, you can go to the View tab and press Shadows here, and then you can change the day and the hour and get a very quick idea of how the shadows move across the scene depending on where the sun position is. And then if you wanted to do more detailed analysis, because this uses a very quick method for the shadows, if you then want a more accurate rendering of the shadows, you can go to the Daylight tab and press New Daylight View. And then this does a much more accurate, using the daylighting engine, projection of all the shadows. And another handy trick you can do as well is to use the 3D view here to position yourself nicely within the space. So if I go to the View tab and press Camera View Setup, I can pick the eye position where I want to be positioned and the target position where I want to look, and then set the height of the camera. And this is quite a handy trick, which I use quite a lot when I'm trying to understand the daylighting in the space. And then once you've got your 3D view set up the way you want it, if you then go to the Daylight tab again and make a new daylight view, it will set the new daylight view to have that same view that you had in the 3D view. And then you can explore the shadows there. So I'll switch back to my PowerPoint briefly and walk you through next what you need to do to prepare a model for daylight analysis. And really, the only thing you really need to do once you've got your space zoned, which you would have done for any other sort of analysis you need to do, really, is to just set up the material properties. That is the reflectances and transmissions of the materials in the model. And then I'll show you how to do basic calculations like daylight factors, vertical sky components, show you some of the reports and how you can get those daylight factors into the building simulator. So if I go back to this view, if I click on material properties here, then this brings up the dialog where you can set your reflectances and your transmissions of all your materials in the model. And we've got a layered approach to it to make it quite quick and easy to set up the properties. So for example, if I change the glazing properties here, that would change the properties for all the glazing in the entire model in one go. But then if I wanted to change the properties of an individual window, I could do that too on the window tab. So I could add, for example, a new one here and then pick, say, the curtain wall and then change those properties separately. And then this will override the default, which is basically set in this tab. So there's this layered approach, and that makes it quite quick and easy to set that up.
So it's basically types in that
Yeah,
first table.
yeah.
So you're literally just giving for each type, but then you can dive in and change the individual elements. Got it.
Yeah, and you can see the types. If you open the building elements dialog, you can see the types there by ticking that box. They're all listed here. And then once you've done that, if you want to do a basic daylight factor calculation, you can just press new calculation here and hit run. And when you're on this dialog here, you can choose the sky type for the calculation. So generally, the most commonly used sky is the CIE sky, and you can choose whether it's overcast or clear sky if you wanted to look at how the space might react to a clear sky with a bright sun, and you can change the day and the hour of the calculation. And then the properties such as how often you sample within the space, that's represented by the grid size there. So you can change that property, the area margin from walls, so you don't account for being too close to the window, and the working plane height. And then you've got the accuracy options here. So the accuracy options in TAS, there are 5 options. Actually, I have a slide for it. Let me show you this slide. So you have the no bounce option, the one bounce option, preview, daylight factors, and detailed. And the no bounce option is, as it sounds, it basically just does one step of the solution for the radiosity calculation, considering just direct light only. And then with the one bounce option, etc., you start to account for more interreflections within the space. And these options that we've chosen, they've been designed such that when you increase the accuracy, you only ever account for more light. So when you were dealing with daylight factors before CBDM came in, really what people generally cared about is, are we reaching a minimum daylight factor? That tended to be sort of the target. So you could always start with a coarser calculation and then increase the accuracy to save doing unnecessarily long simulations if you were dealing with a very large model. Back when this was first implemented, the computers weren't as powerful as they are today, so that was more of a concern than it is today. So you can see here in this table, the preview accuracy accounts for about 70% convergence. The daylight factor accuracy is 95% convergence. And then only really need the detailed accuracy if you were dealing with really complex spaces with lots of interreflections and things like that. But you can see that the daylight factor, how it increases here. So it does only ever increase with the increase of the accuracy.
I'm guessing if the surrounding surfaces are sort of white or shiny, that means there are more bounces, and you probably need to go a bit longer.
Yeah,
whereas
exactly.
If they're nice and absorbing, boof, job done.
Exactly. So once your daylight calculation's done, so that's finished, that dialog automatically closes on its own. Then it automatically opens the daylight results sidebar here, and you can tick the box here to view the results. And you can have multiple results in a single file, which is quite useful because then you could make a tweak to the model and compare the design. So that's quite handy, and you can set a name for the calculation to help keep track of what you've done. And you have a tabular view of all the results here. That shows the daylight factor, the uniformity, the percentage above the base lux level that you set, and these results can be copy and pasted into Excel for further analysis. You can also view lux values instead of daylight factors if you want to, and if you click this little button here, you can change the scale. So you can play around with the values here to look at different bands of lux values if you want to, or daylight factors. And we also have the ability, once you've done a daylight calculation, if you wanted to get this information into the building simulator, then if you select the calculation and press the little save button here, that save button saves them for building analysis. And then those values for that calculation will then be exported to the building simulator, and you can see those values by clicking this button here. Just if you wanted to confirm which values exactly are going to get sent to the building simulator. And then when you export and merge your 3D model with your building simulator file, those values come across automatically. And then the other things that would be nice to show you would be the reports. So we've got some reports here. We've got the daylight report here. If you run, I was running it on my local machine. Let me find my other machine.
Andrew, while you're doing that, we have a couple of quick questions which are relevant to this section. Yeah, so attendees asking about daylight factors on large models with reflectance convergence. Sometimes the calculation times are quite long, several hours. Any tips and tricks to kind of optimize this and shorten that?
Yeah, so I mean, it depends again what sort of analysis you're doing, but I find that the way that the calculation scales, the more geometry you have in the file, the longer it takes, because it scales with the number of surfaces in the model. But for example, if we look at, so this is our training course model, and this is a good example. If I wanted to calculate the daylight factor for B1 Office 9 here, if this was a solid wall and it wasn't connected to all these other spaces, running it on the whole model would be longer than if we were to just delete all this geometry and just run it on B1 Office 9, because as you can see here, there's nothing outside these windows that's going to be affected by what's going on behind. Like the windows are here, so nothing of this geometry behind it is going to affect the daylight reaching that space. So there are some things that you can do there to simplify the model. And again, if you depending on the sort of analysis you're doing, if you're not interested in a metric where you're worried about it being too bright and you're worried about it hitting a minimum value, then you can start with a lower accuracy and increase. But yeah, we're also looking at other ways to speed this up, and we'll come back to that later on in the presentation. So yeah, this is our training course model, and if I go to daylight reports, this report here is a daylight factor ranges report. So once you've done the calculation, if you want to summarize the results and how the average daylight factors fall, then you can generate that report there. So that's one of the reports. We've got a window report, the BSEN 17037 report. That one accounts for how many hours of or how much sun a window receives on a specified day. So for this one, you can pick a weather file and then choose which windows you're interested in. So actually, I'll run it on all the windows because it's quite a quick one to generate that one. Then we simulate, and it will calculate. Maybe make this bigger.
Thank you.
It will calculate. Yeah, there we go. Sorry about that. Yeah, so it will summarize all the windows in the model and how many sunny hours there are for each window, and it'll do that. I generate a nice report which you can then save to PDF or Excel. Then there's another report. It's got quite a lot of reports. If we open the task manager and click create report, there's another one here, daylight report, and that one actually I did pre-generate that one, I think. No, I didn't. That one generates diagrams of the space with the results in them, and gives you a nice table summary as well.
Well done, Andrew. I always find these sort of demonstrations really difficult because you're trying to drive the software, think about the software, and talk about the software at the same time.
Yeah, I discovered a few reports that I forgot were even in the software actually, because we've got so many bits to the software now. But yeah, so this is a nice daylight report as well. This one's quite nice because not only does it give you a nice diagram, but you also get a summary of the reflectances and transmittance values that were in the model at the time that you generated the model. So it's a really handy one for referring to later. And yeah, there's another report in here as well, which basically does a summary of, again, it's a bit similar to the BS 17037. It gives you a summary of how much direct sunlight the window can receive when weather's not taken into consideration. So the other thing I'd like to show you before we move on is to try the Teams sharing windows in the way. Is a rendered daylight view because they're quite handy. So if we go back to the daylight view that I showed you earlier, if you press the view settings button, you can do a full rendering, not just simple shadows, but you can use reflected light in your rendering as well. So if I press reflected light here and then choose a quality setting, and then I'm going to use a clear sky and pick a day and an hour, and then click render, then this does a proper full daylight simulation and rendering of the light in the space. And that can be really useful when you're doing things like CBDM and you're trying to improve your CBDM result. You can get a real understanding for how the light is bouncing around the space and then make changes to the design to improve upon that. So I think
that will probably impress clients too.
Yeah, it's nice. It does look nice. They do look nice. Oh, the other thing that you can do in here as well, actually, I forgot to mention, in the new calculation window when you're doing a daylight calculation, you can also do vertical sky component calculations here. So you can pick this option and hit run and show results on plan. And this gives you the vertical sky component results, which is like a ratio of how much light the center point of the window receives in relation to a horizontal surface at the same location. So yeah, that one's quite handy, and is another metric that's widely used. So if I hop back to my PowerPoint, next I'll show you climate-based daylight modeling, which was the next evolution, and our CBDM results viewer. That one's quite a handy tool that not a lot of people seem to know about or seem to use that widely, but I find that one very valuable. So for that demonstration, I'll use this model here. This is actually, Ian, you'll recognize this model. You made this model when validating our CBDM implementation.
It's not my fault. I think we used this model because it was one that had been validated previously for CBDM by Mardeljevic. So yeah, that was the reason for doing that. So we could compare to previous results with a totally different package.
Yeah, exactly. So to do a CBDM calculation, it's very similar. Again, you set up your material properties as before, and then you just press the CBDM wizard button here. So I'm just going to show you, I'm going to call this one test. So we had an option as well before multi-core computers were very, very, very commonplace to send the job across multiple computers in a network. But we also have this local only option now because it's a bit less commonplace and computers are quite powerful now. So yeah, sorry, on that page, you can set your display grid size and area margin from walls, etc. Give the calculation a name, the start hour, end hour, and your CBDM illuminance bands. And then you can pick your weather file. So I'll just pick London. And now it's calibrating the weather. And then we can choose our zones that we want to include. This is a little search here. So what I told Paul this the other day, what you can do if you have a long list of zones here, you can very quickly filter them. So for example, you could include all zones by default, and then you could type in, say, for example, circ for circulation, and then exclude those all in one go by right-clicking there and clicking exclude. So you can very quickly remove the zones that you don't need in the analysis to keep the analysis nice and quick. And then once you've done that, you can press this save button here, and you can save that list to a file, which you can then use if you ever have to do another run, just to make things a bit quicker and easier. And then I'll set this running. So our CBDM method is quite unique, isn't it, Ian? Or it seems to be fairly unique. We sample points throughout the year when we do our CBDM calculation to keep the calculation nice and fast.
Yeah. So basically, we split it. I think we only do one diffuse sky calculation because obviously the lux levels inside the space are going to vary with that sort of diffuse sky lux. And then we do, I can't remember how many now, but I think we do 7 days through the year in the center of each month for the direct stuff, and then obviously each hour through the year you're doing that balance based on the weather data of how much direct is there compared to how much diffuse, and then you just superimpose those two solutions on top of each other to get the daylight, the complete daylight map through the entire space for each hour through the year effectively. So yeah, but I think there's another package that does it in a similar way, because I thought it was unique as well. Andrew, and it's probably unique in some ways, but
yeah,
I think I found
parallel
another
development,
package.
like you said. Yeah, exactly. So yeah, that's finished now. So yeah, this one's multi-threaded. So if you've got, because all the different days that we're sampling are completely independent, basically, so it's very easy to make this run a lot quicker. If you've got a machine with lots of cores available, it will go quite quickly.
You don't have thermal mass, is what you're really saying,
Yeah,
which is
yeah,
the problem
exactly.
with what we do. How many cores has your PC got, by the way?
This one's got 32, but this virtual machine's got 16. So then when you get to this page in the wizard, you can choose to save the CBDM results file, and I would recommend always saving that one because it's really useful for understanding the space. So I'll show you that in a minute. So then we press next. File exists, so I won't overwrite it. I won't save it that time. And then the report will be generated. Now you can regenerate this report at any time. So you start with a summary of the overall results for each zone, but then if you scroll down, you get more of a breakdown, again with that useful summary of the inputs there. And yeah, so you can run that through by pressing this button here. And actually, if you want to, you can even put your own images in instead of the ones that were automatically generated, should you wish to. So let's show you the...
Antonino just asked, is the wall thickness taken into account? And as far as I'm aware, what you see is what you get. So those images that you showed previously, yes, the wall thickness is in there. So
yeah, the wall thickness, yeah, that is definitely taken into account, because we have building element thicknesses by default in TAS. So now I'll show you the CBDM results viewer, which is quite handy. So when you open this, it'll ask you to pick a weather file. As long as you've got the same latitude and longitude, you can actually run the CBDM metrics again with a different weather file if you want to, without having to do the full simulation.
So you could do different years?
Yes, exactly.
Didn't know
so
that.
That's quite handy. Yeah, so that's quite handy. And again, you can play with the thresholds as well. So once you've done the calculation once, you can, if you wanted to, you could change the UDI metrics and the various thresholds and the period that you're analyzing, as long as it's smaller than the original window. So that can be quite good. But yeah, so this is really handy because you can see, if I turn off the UDIA one here, you can quickly see UDIS and UDIE. You can see the months in the year where the space is performing poorly at a glance, which is quite good. And then you can zoom in on any of those. So for example, you can see like it doesn't perform particularly well in December, which is not surprising because the sun's quite low in the sky and there's not as much daylight in December. But we could zoom in there and then we could change to a weekly mode. And we could pick one where the space isn't performing particularly well, go to hourly. And yeah, it's really interesting. Like, for example, you could zoom in here and identify, the 29th of November at 2 p.m. There's quite a bit of excessive there. And then what you can do is you can go back into the 3D modeler and you can, if you go to view, you can then find that day in the year. I'm not sure what day November is, but yeah, we could say do 3, 4, 5, for example. And then we can actually look at the sun in the space. And when you do that, for example, in the past I've identified periods where we're getting an unexpected amount of direct sunlight where it's excessively bright, rendered a view, and then seen the sun patches and how they're coming into the space. And then you could do things like put an external shade outside the building or a light shelf or something like that to try and reduce those hours where you're getting too much light, or the hours where you're getting not enough light and it's a bit too dark. There might be hours where you can try and do something to increase the amount of light at the back of the space.
So well. you could literally change the blind systems out the front of the window, depth,
yeah.
thickness, distance between the fins, all that kind of stuff. Yeah, okay, makes sense.
Yeah, in fact, I've got an image of that on the next slide. Actually, I'll show you that in a minute. And then when you're in the CBDM results viewer, this is where you can do some of your BREEAM metrics as well. So if you press analyze here, then you can do the metrics where you calculate the amount of area that receives at least, say, 300 lux for 2,000 hours a year or more. And you can look at the minimum daylight illuminance. And then you can press the report button there and it will generate a summary report for all the zones in the model with these settings. So that's how you can do that BREEAM metric. So yeah, that's it for the CBDM results viewer. If I go back to my PowerPoint, and now I'll show you another really useful tool for the daylighting, which is importing shade surfaces. And this is really, really handy. So that's basically what this is taking geometry from a 3D DWG or a DXF and importing it into the model and using that for shading purposes. So that's really good for modeling things like light shelves. It's really good for modeling things like trees, cityscapes as well, which is really useful for if you're doing something like BR209. And actually for this, you see this image here at the bottom. This is one of those images I identified in Hour where we were getting quite a lot of lux in the space from the CVDM results viewer. And then I did a rendered daylight view of that Hour to see what that was looking like, where I could then think about how to improve that result. So if I go to Rhino, so this is a 3D DXF. So to generate this, if you go into the 3D modeler, and you create an analysis view, then if you go to export CAD, you can export a 3D DWG or a 3D DXF. So I did that. I've just done it again by the looks of things. And then if you go and then open that in, so I used Rhino, but you can use AutoCAD. It comes through with all the material layers. Then I created a new layer called light shelf, and this is where I've added this light shelf here, and I can position that really nicely in relation to the space. So you don't have to export TAS geometry to do this process, but the advantage of doing so is that you can position your shade really, really precisely in relation to the geometry in the model. And that can be really useful if you've got like a really, really complex shading system. Yep. So if I go back to the model now, and then I import a drawing, I have to find the drawing. Yeah, so if I import that and then map it, then once I've mapped my DWG, I can press this button here, which is import 3D shade surfaces. And then what I'll do is I'll go to the layer selection and I'll only select the light shelf layer. And then I'll press apply and then press OK. And then that will import the by default, I need to refresh the analysis view. That will import the layer there. It will come through as a separate story, all the geometry on that. And it comes through as black because that's the color that was in the DXF file. But if I wanted to, I could change the property of that light shelf. I could make the color green, for example. And because that comes through as a building element called light shelf, I can then set the material properties for that if I want to. So I can go and click material properties here and change the reflectance. So, for example, I could
and transmission, because you could have like an awning which is sort of very slightly transparent, that kind of thing.
As far as I'm aware, yeah, exactly. Fabrics, so you can change the properties there, and that will be then taken into consideration in your daylight calculations. So yeah, it's nice because you can do quite complex geometry. So you could have a really, really complex external shade and modify it quite nicely. You can define shades in TAS quite simply using the new shades feature. So for example, I've opened this here. You can specify the number of fins and the angles and things like that. And I'll show you that in a bit more detail later. But yeah, if you're doing something really, really complex, then it's quite nice to be able to draw it any which way in Rhino or in AutoCAD and then bring that into TAS. So that shade surface import is also really useful for doing BR209, the right of light analysis and right of light analysis. So the right of light analysis in TAS, not a lot of people have heard of it, but there's a guide which has a number of calculations in it which are designed to quantify the impact of a development, a change to a development or a new development on existing surrounding buildings and properties. So here, for example, we have two models. They're based on the same model, but as you can see, the building in the middle has changed. So the top geometry, we usually refer to that as the existing geometry, and then the bottom one, we tend to refer to that as the proposed geometry. So the idea is so all of this geometry has been imported from a 3D DWG, and then what I've done is I've set spaces within this imported geometry as spaces that I want to analyze. And then we have a wizard called the Daylight Analysis wizard, which is designed to run these calculations, such as the vertical sky component, the annual probable sunlight hours, daylight distribution, permanent overshadowing, and equivalent first zone, run these calculations and compare how the result changes between the two models. And there's more information about these calculations on our website. Annual probable sunlight hours, for example, we've already talked about VSC, but annual probable sunlight hours is the amount of hours of sunlight a window receives, for example. And that takes into consideration whether daylight distribution is the amount of the space that can see the sky, for example, to see the sky directly. Permanent overshadowing applies to external spaces. So if you've got like a garden, you can say how much your daylight the garden's going to receive is going to be impacted by a change to a development. So to launch that wizard, let me jump back to my virtual machine. You just go to Utilities here, and then click on the Daylight Analysis wizard. Whoops, that's the wrong one. And then you pick your existing and proposed model.
I should just tell you, everybody who hasn't done a Teams presentation like this while you've got your screen sharing on, your computer just starts to behave really slow and clunky. I think it's all to do with the fact that Andrew's sharing his screen. So yeah, it's not as bad, maybe not as hard as you might think it is.
Yeah. Once you've done that, you can. When we're doing this right of light stuff, this is really usually it's dealing with massive models. You've got a lot of zones here. I mean, look at how many zones are in this model. I'm not sure exactly how many there are, but there are a lot. So on this page, you can set tags and things for helping you organize your results. So you can specify room uses and add more room uses, and then tag zones with different room uses and things like that. Just a way to help you organize the results when you get out into Excel later, because there are just so many zones. And then on the next page, I believe we specify our properties. Yes. So of the calculations we want to do, this is where we specify the properties that we want to run those calculations using, the parameters. So for example, you can change the grid size, working plane heights. A lot of these will be quite familiar. For the permanent overshadowing calculation, you can choose the day that it runs on. For annual probable sunlight hours, you can pick the weather file. So yeah, I can pick a weather file here. And then on this page, you can choose. So this summarizes all the settings that each zone is going to be run under, and you can override some of the settings if you want to. And for example, if you wanted to exclude certain calculations from certain zones, you could select them here, right click, and then turn those calculations on or off for those zones. And then when you press next, the wizard will start generating the calculations that need to be performed to get you the results that you need. And then you just hit simulate. I'm not actually going to run that one because it takes a couple of minutes and we're a bit tight for time. But once that one has, yeah, there's a lot to daylighting in TAS. But once that's run, you get these CSV files out, which I probably should have made sure I had Excel on this machine. But we also have a daylight analysis results viewer as well. So that produces this file here, this TDA file. And if we open that, then we get, it's just opening, it's quite a big file, this one.
Yeah, Jason,
and we've got some questions on this section.
Oh,
yeah,
Jason,
sure. Jason just asked, how do you zone an imported DWG, which is a good one.
Yeah, so usually what I do is I import it's actually quite a good question. So I import the geometry as it is, and then in the 3D view, when you've got the imported geometry visible, you can actually use the 3D selection tools to select walls. So then you can click on a wall and copy it to a story, and then you can do that for the walls that you're interested in, and then just zone that space. And yeah, that's one way that you can do that. Yeah, I think that's how I did it when I originally did that model. So yeah, now that this is finished loading, so we've got different reports here. So you can have a report of all the annual probable sunlight hours results in one place. So again, if I click here, then it generates these. I'll make it bigger. Sorry, it generates these nice diagrams showing you the space where the windows are for the existing and the proposed. Because, for example, you could actually even move a window if you wanted to and compare the differences. And it shows you the the result for the existing and the proposed and the amount that it's changed. So you can see here, for example, the result is slightly different, but it's very, very close. So you can do that for all of the calculations. We've got equivalent first zone here. And it generates these contour diagrams, and you can see, let me just find an interesting one. Yeah, so you can see areas where the amount of received light has been reduced. So the green is the existing, and the proposed is the red line here. And again, you get a daylight factor report, daylight distribution. You get all of those, and then you can also generate reports for a given zone. So I could pick one Rye lane, and then all the calculations that have been done for that zone also go into their own report and are summarized, which is quite handy. So I'm conscious I'm going quite quickly, so I do apologize, but yeah.
Or it's being recorded, it'll be uploaded, people can play it back.
Yeah, exactly. But it's just to really give you an overview, really, because there is quite a lot that you can do. So yeah, feel free to get in touch if you've got any questions about that. Another nice little quick sort of case study just to show what else is possible. I had the idea of modeling something like Schiphol Airport from Amsterdam, which is typically quite highly glazed, and I mean, this one has like a shade overhang, almost like a brise-soleil, and then it's got this external shading here for passengers to walk under so they don't get wet when it's raining and things like that. So I made something kind of vaguely similar in TAS, and then for this purple overhang, I did this in Rhino and just imported this surface here. And then I thought, well, what if we try to improve the daylight in the space using our optimization tool? So things that you can vary and might want to vary, you can vary the transmittance of the windows. You can vary the number of fins on the shade here. So when I showed you that shade dialog earlier, you could enter the number of fins and the angle of each fin, for example. So you can change that with the optimization tool, and the fin depth and things like that. So what I decided to do is I thought, okay, well, what if we varied the light transmission of each row of windows? So what if we could have each one of these rows transmittance as a different variable and vary that, and also vary the angle of that shade that you saw outside of the window.
The horizontal one, yep.
Yeah, exactly. And then I did a clear sky. And then I sampled results for the March equinox, the summer and the winter solstice, and I used hours 9, 12, and 15 because I didn't want to just do one point in time. I wanted to do several clear sky days throughout the year so that I would get a good overall annual sort of result. And then my cost function also tried to produce a result with good uniformity and an average lux above 300. So I did a parametric run initially just to get a feel for the result. I did 2,900 simulations, and then I did a proper optimization run where I let the algorithm intelligently pick what to change. And that only took 60 simulations to hone in on the result. And the result was this. The result was the top two rows in the space should be quite transparent. They should be quite clear. I think they were 90% transparent. And then the bottom three rows of windows should be quite dark, sort of 20%, 30% light transmission. And then the shade angle should be exactly 57 degrees. And that would give you the best overall uniformity whilst giving you at least 300 lux average luminance in the space. And the interesting thing is, if you did that same simulation without varying each row of windows as a option as their transmittance as a variable, then the best result is actually a shade angle of 90 degrees, which is basically just a solid overhang rather than having a nice angle there.
How long did they take, Andrew? Sorry, just curiosity, the 2,960.
I didn't actually time it. It was quite quick. I think I went off and made a cup of tea, and by the time I came back, it was done.
So we're talking minutes, not hours.
Yeah, it wasn't too bad. And again, the 60 simulations, that was even quicker. It depends how many cores you have available on your computer as well, because again, that scales really nicely with the number of cores. But you can see the result here. So this is the lux level result, unoptimized. So you can see you've got really, really bright patches, and the uniformity is not very good. And then here we've got the optimized result. The average illuminance came right down to 980, so you're at less risk of glare, and the uniformity went from 0.35 to 0.47. So yeah, a real improvement in the uniformity. And you should also see that reflected in the, no pun intended, reflected in the CBDM results as well. So I did a quick CBDM result just to see what that result would look like, because again, you could do this with classrooms and schools and other offices and other spaces. And here you can see the original UDIA result. The space near the window was actually much too bright for quite a lot of the year. And in the optimized version, you can see it's much more uniform. So the UDIA result went from 74 to 85, so that's quite a big improvement there. So yeah, so that's a very quick sort of overview of what we have in TAS at the moment. And then what I'd like to talk about now very briefly is where we want to head with our daylighting implementation at the moment and what we're hoping to bring in the near future. So I mentioned earlier, there was split flux, radiosity, and ray tracing. And Radiance is a very commonly used package. It's used in quite a lot of building simulation software. As graphics cards are getting more and more powerful, they're being driven by the gaming industry. There's this real sort of demand for real-time ray tracing from the gaming industry. So these screenshots here, these are from the NVIDIA website, and a lot of games now have real-time ray tracing in them. So you can see the top images with the ray tracing off, the bottom images with the ray tracing on, and you can see some of the features that, again, we are very interested in when we're simulating light inside of buildings. So you can see, for example, the gun here has reflections from this light. It's illuminated there. You've got some really nice shadows. I mean, I know the geometry is slightly different. You get some really nice shadows from the leaves here in the trees. This building here is getting a lot of interreflections. So this is for a game to be performant enough, this needs to be really fast, and that's something that we can take advantage of if we start switching to a ray tracing based approach. So what we're thinking is what we will do is we'll probably offer both and keep our radiosity solution, because our radiosity solution is based solution is still really good and really good for diffuse. But the downside is the scalability. So as you're scaling up with our current implementation, if you end up with really large geometries, the simulation time can increase quite rapidly. Whereas it seems as though with a ray tracing based approach with these graphics cards, which have hundreds of ray tracing cores, the scaling is much better. So it'll be really good for really big models. So this is the scene from earlier in the presentation, and I rendered this again using Radiance, and as you can see, the results are quite similar. So that's promising. And the simulation time for the top one was 10 seconds. The Radiance one actually was a bit longer. It took maybe three minutes. But for a much bigger scene, you might see the simulation time flip, and you might see that the radiosity would be much slower than the Radiance version. So yeah, so in certain circumstances, the calculation will be a lot quicker. We can also do things like introduce glare analysis as well, and we can model more complex materials if we switch to or offer a ray tracing based solution as well. So we could model
shiny stuff.
Yeah, really shiny stuff, and bidirectional scattering functions and things like that. But yeah,
all to do with the specular stuff. Yeah, exactly.
Yeah, exactly. But yeah, so radiosity solutions are still quite often quite preferable, just because building interiors tend to be dominated by the diffuse. But it's nice to be able to offer an alternative, which might be useful in certain circumstances.
Let's be honest. The reason we're considering Radiance as the ray tracing solution, which previously is software based, has not been very good, is the fact that NVIDIA are throwing 512 cores into these GPUs, which are less than £1,000. Yeah, it's crazy.
Yes, exactly. So it now becomes a lot more feasible, because back when we started with the daylighting and it was first being introduced, there was nowhere near this processing power. So a proper ray tracing solution that would give you really accurate results, especially when it comes to the diffuse, it was just impractical. But now, with the direction it's heading, it's becoming more and more practical. And yeah, when we're comparing these two images here, just if any of you are comparing them, you have to remember these are high dynamic range images. So depending on your exposure, the result will look quite different. So this is the same image here that I'm flicking between, and I'm just changing the exposure, and it really does change the way that the image looks. So just bear that in mind when you're doing a comparison. So that's where we are heading at the moment. I think I've left just about enough time for some questions.
Yeah, well done.
Yeah,
10 minutes.
Yeah, yeah.
Andrew,
Just about
perfect.
perfect.
Appreciate you. Yeah, appreciate you getting through a lot of content.
There's a lot. Yeah, there is a lot. Yeah, there is a
Thank you
lot.
for that.
Yeah.
I'm also pleasantly surprised at how much capability there is in TAS for daylighting. I don't think this is widely appreciated or understood in the market out there. It's probably something we need to get better at communicating. Certainly, this webinar is a start for that. But should we take some quick fire questions, Andrew?
Yeah, of
and
course.
Ian? So let me go back. There's a couple of questions related to the import of shades. The example you showed from, for example, Rhino. So a question is, that shade that you imported and it came as a building element, presumably you can edit that in TAS if needed to, or is that fixed? And related to that is, you imported the shade. What about importing other objects like trees and streetscape stuff? Is that the same process?
Yeah, it's exactly the same process. So well, I can show you actually. So this slide.
Yeah, when Andrew's doing this, we got sent a tree model and they'd modeled every single leaf. It was a nightmare.
But it works, but it's
slow.
A bit overkill. Yeah, a bit overkill. But yeah, so again, this is there's a website. I think you can enter some coordinates and enter a region and then export a section of cityscape geometry, and then it imports in exactly the same way that I showed you before. So you basically just select the layers that you want to import and import those surfaces.
Yeah.
Now, once they're in TAS, your editing options are limited. It depends what you want to edit. If you want to change the imported geometry, the shape of these surfaces, it's best just to do it in the source package, because it's not really our 3D modeler is designed around making really, really good watertight volumes, because that's what's needed for building simulation analysis. That's not needed for daylighting. For daylighting, things don't need to be necessarily for the spaces that you're analyzing, it does, but for things that are casting shadows, you can have a surface. It doesn't need to be part of a watertight, really, well-defined space. So there's sort of a different set of needs there. But you can change things like the reflectances and transmission values of those imported surfaces.
And that will be based on the layers, is that right?
It doesn't even have to be based on layers, but yes, once they are imported, that's the easiest way to do it, based on the layers. But you can also, I'm not sure if I've got one to hand. Yeah, there we go. When you're in the 3D view, you can assign a different building element to that surface if you want to. So you could have 3 or 4 different surfaces in the same layer in the imported file, and then you could use the set element tool to change. Yeah, and you could make your own building element for them and then assign them different properties and things like that. So there is some editing capability in there to control the properties of those materials that are coming in.
So basically, from your source model, you could just draw all of those blinds or whatever in, and then within TAS, you can then change the properties for each of them.
Yeah.
Great. Sorry. I'll shut up.
And related to that, Andrew, when you imported the city model, the context, can you do any calculations on those models, like the VSC on the surrounding windows? Or if you
specify where the windows are, then yes, you can. So when you import a 3D DWG, do I have one here? I might have one. It doesn't necessarily have necessarily have windows in there. It might just have holes where windows should be, for example. But then what you can do is you can select a surface which contains one of those holes, assign it to a story, and then add a window in TAS where that hole is.
Right.
And then you can analyze it. So there's
a way of doing it.
Yeah, there is a way. Yeah, exactly.
We have Tang asking a very specific question around CBDM results being used as proof for EN 17037 compliance. I don't know if you're familiar with that standard.
I'm not. 17037 is there's 2 parts to it, I believe. There's the amount of light each window receives, the simple metric, which I showed you here, this report, and then there's also a glare aspect to it. So I'm wondering if they're referring to the glare aspect. But yeah, that's something that's something we want to do glare using the annual glare probability metric, and that's something that we're working on implementing, which will make it easier to do the full BSE and 17037. So that's something that's kind of in the works. There is a way that you can say that. So when you do a CBDM calculation, there is a a consensus that if the lux values in the space are over 3000 lux, then that increases your risk of glare. So that, you know, but again, we'd like to implement the full glare metrics for easier, more accurate sort of analysis of the risk.
Talking of glare, there was a question early on. You kind of covered it. This is a broader question about kind of timing of upcoming features and release, and the question was specifically about glare probability. So what's if you take a step back now from all the features, what's the product roadmap looking like in terms of when some of these features will be coming to TAS?
Yeah, I mean,
we need to clone Andrew, basically. If we could clone Andrew, it would go twice as fast.
Yeah, and
others, by the way.
It's interesting because it's an area of research in a way. We don't want to just use radiance as is and blindly trust it. You know, we'd like to validate, because we've extensively validated our Lightworks implementation, our current daylight engine.
Yeah.
And radiance has a lot of different parameters, and it's so easy to produce bad results with the wrong parameters. You know, we want to make sure that we validate everything properly, and also make sure that all of our inputs are comparable to, you know, what they should be. Everything is set up properly. So that is an area of research, really. And the other problem is, because lots of packages use radiance, if there was a mistake with radiance, if there was a problem, how would you know about it? You know, there's not enough validation against sort of real world results. There might be a consensus because a lot of packages use radiance, but that doesn't necessarily mean that they're all correct. And even you know, while I've been doing some of this implementation, I've discovered that some of the sky definitions in radiance aren't complete for when you do CBDM. There are terms that are missing that should be ideally should be included. So we will add those in before we include radiance and have a radiance solution in the software. And also, as you saw, there's so many different bits of daylighting in TAS. Like, we've got all these reports, we've got the CBDM, we've got the CBDM results viewer. We'd like to make sure that you can choose whether to use the Lightworks based or the radiance based implementation in all of those different places. So there's a bit of work to do there, but it's something that, so we might do, like, maybe we'll do like we'll build it up in stages. And maybe start with like the priorities. For example, glare is something that, you know, people are increasingly interested in, so we'd like to provide a solution to that quite quickly.
Just to go back to the validation quickly, one of the first things we did when the first daylight stuff came out was in the offices in Stony Stratford, there's a nice little sort of roof light and a small sort of area, like corridor area. And I literally got up on a set of steps and had the lux meter at various heights from the sort of ceiling level right the way down to the floor. Then we put all of that into the software, ran the daylight calculations, got the lux values, and went, yep, that looks good. We're happy. We're within a few percent. So yeah. Obviously, we had to make assumptions about transmission of that roof light and that kind of nonsense. So there was a bit of give and take, but we got the right distribution, which was the most critical thing from our point of view.
Andrew, on the CBDM tool, can you change the hours for simulation? Like, if you want to set it to school hours, you can,
Yeah, exactly, yeah. There's a little drop down. You change it from priority schools to other, and then you can choose the start hour and end hour and time step, for example.
Okay, brilliant. Is there anything else you wanted to show, Andrew, before we wrap up?
I mean, I think I think the best thing is, like, if you've got TAS, have a go. That's the best thing to do, really.
And if you haven't got TAS, ask us and have a go.
Because if you haven't got TAS, then just contact us, and you can get a trial from the website. We'll give you a trial to contact us. But there's so many bits to it. I would say, you know, if you haven't already had a look at the CBDM results view, it's quite interesting. Because it really helps, rather than just sort of like making a guess on how you can improve the performance of the space. It's really useful for really sort of understanding it.
Yeah, directing the design, that's what it boils down to.
Exactly. Yeah, exactly.
Okay, fantastic. We're top of the hour there. That was fantastic. Thank you for all the questions. And again, Andrew, you put a lot of effort and work into preparing this webinar. Thank you to Ian and the other guys who joined. A couple of quick announcements from my side. We have a webinar coming up on the 28th of April, from building physics to simulation outputs. We're going to take you right back to where it all started and have a look at the future. That'll be Ian driving that one. You might have seen our 1985
and
Back
others.
to the Future post. And TAS will be exhibiting at the SIPC Technology and Innovation Showcase on 17th June. in London. So watch out for that. We'll be sending more details. Ian, I'll hand over to you for some closing remarks. Thank you.
I was around in 1985 and I was 23. So there you go. No. A brilliant job, Andrew. Absolutely excellent. There's no way I could have done that.
Well, hopefully
again,
it's useful.
Oh, hugely useful. I think the most important bit, if you're going to do it, Nagman, is taking the video of this session and uploading it, because I'm sure quite a few of the people watching are going to be wanting to take another look and step through it a little bit more slowly. So
Yeah, we did go quite quickly, but at least you know what's possible now, and then you can ask us for a more detailed, slower demo if you want one.
That was a lot to cover, Andrew, and well done in getting through it in an hour. So no, that's excellent. Yeah, and again, it's embarrassing to say, you're saying, oh, some of the customers don't know about this. Well, some of the features Andrew showed us, I think yesterday or the day before in the run through, I was going, I didn't know we had that. So yeah, don't feel bad if you didn't know about it. Good. Are we all done, Nagman?
Yeah.
Great.
Yeah, we're good.
All right. Thanks everyone. Thanks for joining.
Excellent. No. Thanks, Andrew. Thanks everyone.
Bye.
Cheers. Bye.